This talk is about setting quota, which is a tricky undertaking. And what we're specifically going to show is that is how to set a quota rule. That is to say, a quota is an upper limit on catch that's set yearly to determine how much fishers can take out of a particular fish stock. There's been traditionally, before decision rules were brought into play, there was a lot of argy-bargy. Fishers argued with managers. Eventually, the minister would have to decide. It didn't always yield optimal decision-making. So nowadays in South Australia, what we're doing is establishing decision rules, quantitative inputs that come from the season before, pass through some kind of mathematical rule or a table to specify what the quota will be in the season to follow. And the questions we're going to ask here today are, what general principles can we use to simply construct a decision strategy for building a fishery? And specifically, how do we construct harvest strategy decision rules for the two lobster fisheries in South Australia? These are the two zones, the northern zone and the southern zone of the South Australian lobster fishery. Even though this covers a much bigger area, there's a lot less reef habitat and lower densities of pearlists. Here along the limestone coast, the pearlists settling in from off the Southern Ocean are high, much stronger than in the northern zone, and the amount of limestone habitat is enormous along the shelf regions. And so lobster abundances are high in that southern zone. So we're going to present a simple way to construct a decision rule for setting quota. And the underlying principle is, within the normal range, the range where stock abundances can typically rise and fall historically without showing a downward trend, we set the quota in such a way that you remove a constant fraction of the population in each year. So that if population rises, the quota can rise. If biomass declines, you reduce the amount of quota correspondingly. So it's a very simple rule. And we apply this in the normal range, like I said. At lower ranges of abundance, we have to reduce the levels of exploitation. So the first thing we did, the first paper we published on this stuff, had compared this rule where we set quotas yearly under a decision rule based on a constant exploitation rate or constant yearly harvest fraction, and compare that with three very standard approaches to managing a fish stock: fixed quotas and two kinds of size limit. And the outcome is that, considering the economic performance of these four different strategies, the constant harvest fraction dynamically changing quota yields much, much higher levels of economic return to the fishery than constant quotas. Even for all the possible ranges of harvest strategy, this performs better, and certainly much better than the two size-based strategies. So from an economic perspective, you get vastly superior return with a bioeconomic model fitted to a length-based estimator and converted into a harvest strategy simulator. But using all that mathematical structure, we find much better performance from an economic perspective. Now we're going to try to apply this principle, first of all, to the southern zone fishery. There'll be no spatial considerations. And the way the rule will be constructed is we'll use a discrete form. In other words, we'll form a table. So within bands of the indicator from the previous season, which will be catch rate, within each band there'll be one quota. So if the catch rate falls within that band from the previous season, that will establish what the quota will be for the season to follow. And this describes how we will alter things when abundance becomes lower than the normal range. So if we consider catch rate, which is just the weight of lobsters in an average pot averaged across the whole season, in the southern zone that's 1 million pots, so it's quite an effective, certainly a large sample of the population, even though it would be targeting higher abundances. You find that here's how the rule will work. Remember, we're saying a constant fraction removed yearly within our normal range means as abundance rises with catch rate, the TACC, or the total allowable commercial catch, the quota, that also rises linearly. Below an upper limit reference point, below which we're saying, look, there might be some risk that this population is not sustainably fished, that there is a risk to the reproductive viability of the population, at that point we begin rapidly lowering the exploitation rate, or the fraction that's removed yearly, till we get to a lower limit reference point, now sometimes just called the limit reference point, at which point the fishery is closed. So if catch rates fall below that value, exploitation rates go to zero and the fishery is shut until we can establish that higher levels of abundance have recovered. And this is just an example of what that decision rule yielded for the southern zone. This is, say for example, if you have a catch rate between 0.6 and 0.7 the previous season, then you just set the TACC at 900 tons. It's as simple as that. There's other sub-rules involving whether there's enough juveniles coming through, but this is the heart of the matter. Oh, I think I skipped one. No, that's okay. Oh. So there's one more study that I'll describe now, where we take the same principle and apply it to the northern zone, where we're going to establish a spatial management regime. It's still using the same principle. So this is still South Australia. There's Port Lincoln. We divide up the northern zone into three regions. The inner zone, where most of the catch has been taken historically, and lately, nearly all of it. The west coast, where they used to catch a lot of lobsters, but they're very large. The rates of pearl settlement, of settlement of juvenile lobsters is much lower out here, but because the densities are low and the temperatures are high, they grow quickly. And outside of this 80-meter line that you can see, we've established a deep water subregion, which is very lightly exploited. Sometimes people go out there and catch high abundances, but those lobsters are generally not healthy, and the Chinese market does not really want them these days. So here's what we find. From tag recovery data, we know that the west coast lobsters grow a lot more quickly. This is from a maximum likelihood estimator using tag recovery data. And we find that in the west coast, growth rates are high. In the inner region, they're actually still pretty high in the northern zone, more than in the southern zone, whereas in deep water, the growth rates are very low, corresponding to the observed lower survival rates once they put them in tanks when harvested. Now what we're going to do is apply the data from catch logs only in order to estimate biomass, in order to construct the table. I'm going to show you how we do that if I've got time. So what we use is one of two models used for assessment of lobsters in South Australia called the QR model. It was developed in South Australia, and we've tested this model using simulated data. So what we do is take an individual-based model that has no relationship to the way we draw inference using the QR estimator. Lobsters die and grow and die naturally, and then when they die, we count the numbers that die and the weight to produce fake data sets that are similar to what we get from the catch logs of the real fishery, to see how well this model can perform in estimating the quantities we need, notably including absolute biomass. And as you can see, if recruitment jumps up and down like this, where the black line represents the simulated true population, that we get very close agreement with of the estimator, which are those open circles, to the true values. So in this way, we've demonstrated to ourselves with confidence that the QR model can produce quite reliable estimates of absolute abundance, given data that come only from the fishermen themselves. This doesn't require any sample data, and that's why it's needed here, because there's very few samples in those outlying regions. And these are what the fits look like for catches in number and catches in weight for the inner region of this QR model, in the west coast, and in deep water. So again, we get very close agreement with data. So we have reason to think it's probably doing a good job. We know those growth estimates are real, and that was an important input to all this. So we get the following estimates of biomass change over time on a yearly basis. What we first observed is that from 1990 onward, in all three regions, there's been a steady decline in abundance. The northern zone is under pressure these days. And what the other thing is that if I put up graphs of catch, we would see that even though there's greater biomass in the inner region, the catches are much lower still, relatively speaking. So the exploitation rates in the west coast and deep water are much lower. So they're only we estimate they were only taking about 2.5% or 4% since 2009, when effectively they did stop fishing out there, partly because the Chinese market only wanted the small, redder lobsters, which are found predominantly in the inner zone. There, the exploitation rates were 21%. And so we went to the fishery managers with this data and at industry's request, and we were able to say, yes, if you would like to lower exploitation on the inner zone, one way to do it is to try to keep the quotas sensibly lower there, but break things up spatially and allow greater quota to be allocated specifically to the outlying regions so that that's where effort could potentially be shifted. Now, the big question is, how do we determine this target exploitation rate? And the answer is, in the northern zone, what we did is we produced this graph, and each of these points represents the change in biomass over one fishing season. If it's above the line of 0, it means the biomass increased over that season. If you have a negative value, it means the biomass decreased from the start of that season to the beginning of the next. And along the x-axis, we have this exploitation rate, this fraction harvested. So we can, but as you can see, when exploitation rates are lower, the biomass tends to rise, and when exploitation rates are higher, above about 21%, where this crosses the line, biomass tends to decrease. So by this measure, we conclude that around 21%, this fish stock is approximately stable. And the other thing is some of that bioeconomic stuff I showed you earlier, we applied that to the northern zone as well, and that also shows that 20% gives an approximately optimal economic return. So by those two measures, we chose our target exploitation rate at 21%. And in the outer region, to be much more conservative, we set the target exploitation rate at a lower value of 10%, which equals the assumed natural mortality of the population. That's another rule of thumb that's often used when we don't know what to do for what level of exploitation is sensible in a fish stock. Now, the last step to constructing this decision rule table is pretty straightforward, and it can be easily displayed by this graph. Suppose we have a band of catch rates from 0.7 to 0.8, and we want to decide what our TAC should be in that band to fill all the bands of the table to produce our overall decision rule. Then we just go to the midpoint, take 0.75, go up to this line and across, and that tells us what biomass is associated with a catch rate of 0.75. Since we know that biomass is, say, around 1,150 tons, we just take 21% of that, because that's the harvest fraction that we've chosen, and that gives us the quota that we apply within that band. So it's as simple as that. We just take the fraction of exploitation that we seek, compute the absolute biomass, which is possible because we have an estimator that can produce that quantity, the QR model, and that allows us to populate the decision rule table. And here's what the final one looked like. So the limit reference point of points below the upper limit reference point of 0.7, you can see these exploitation rates as percentages in parentheses. Those decrease down to 0, and below 0.5, the fishery would be closed. Above 0.7, you get approximate values of around 21% and 10%, with some negotiations causing it to be a little higher than they otherwise would be. But this decision rule was implemented in 2014, which allowed spatial management to be cast in a decision rule for the northern zone. And that's it. Hope we see you guys at the World Fisheries Conference.